I got involved in groundwater modeling in the early 80s. At the time, I was taking an undergrad in civil engineering, and I was also taking an undergrad in geological science. My interest from the civil engineering part in terms of soil mechanics and also in water, hydrology, hydraulics, it combined very well with geology to start studying groundwater. I became an intern student at at the time a computer lab for geoscience at the Institute of Geoscience at the University of São Paulo. There, I started to work under the supervision of Dr. Bob Cleary, former University of Princeton professor who had moved to Brazil at the time, and also with Dr. Michael Ungs, and who taught me a lot about numerical methods, and we started discussing finite elements and so on. We developed at that lab some tools for interpreting geochemistry, brought some interpretation of geophysical data, and it was basically at the time mostly Fortran. You had to know Fortran to be a modeler. The whole modeling, groundwater modeling, was dominated by mathematicians or very few geologists that knew uh, modeling or programming in Fortran. There was one of the first groundwater models called Prickett-Lundquist Aquifer Simulation Model Plasm. It was a 2D finite difference model written by Tom Prickett and Lundquist from the Illinois State Survey, Geological Survey. And I started to use that model to simulate contaminated areas. Uh, at the time, Dr. Michael Ungs decided to go back to Brazil, to US, and they invited me to take over his position at the university. As long as I stopped my geological undergrad, I had finished my civil engineering and started a master's. So I started a master's in a particular landfill where I did a lot of field work and applied this plasma model for flow simulation, combined with a transport model called MOC, written by Lenny Konikov from USGS. And it was quite advanced at the time, even though it was 2D. And we had a great work published on that. I finished my master's, and before I finish, I start to develop some tools to teach people, to teach the students at the time, to use PCs, because we had received in the lab our first PCs. It was a processor called 886 with a powerful 1 megabyte of RAM and the disks 256. I should say that one of my first jobs in the as an intern student was to take these heavy boxes of perforated cards from the lab to the computer center a few blocks away, leave it there to run the models, and then go next day to pick up the boxes and the printed outcome, which normally would come just the errors, and you would identify the line, meaning the card that had the error, replace that card with the correct one, run again. It was a very time intensive using a IBM mainframe to do that. With the PCs, then we start to do very simple applications, a lot written in Visual Basic, some in Fortran. Start to use these tools. Dr. Bob Cleary at that time was teaching a course called Princeton Groundwater Pollution and Hydrology. And he got the idea, and he is still teaching that today, and it's attended by hundreds of professionals every year. He had the idea of saying, why don't we start offering a course called IBM PC Applications in Groundwater Pollution and Hydrology? So we did. We offered the first one in Brazil to test. Then in 87, I went for a PhD at the University of Waterloo. In January 1988, we offered the first course in US called at the New Jersey Department of Environmental Quality. That was January. In June, we offered that course through National Groundwater Association. It was a success. We would teach from word processing. At the time, there was a program called WordStar, that before the Microsoft Word, to Excel, to basic applications of PC, because people were just getting used to it. But it was to groundwater. So I had to develop some specific applications. I got a book by Kinzelbach, Professor Kinzelbach from Germany. There were some programs there in Visual Basic. I got those programs and put in the PC, so we had something to run. But it was still frustrating because you would set up, for example, find a difference model. You'd say how many rows you want, how many columns. Okay. Then heterogeneities. It was very time intensive to prepare any kind of realistic model. Imagine real models. So then, at the time, I met a student from a colleague at the University of Waterloo called Thomas Franz. He had experience in path lines because he was a former student of this Dr. Kinzelbach in Germany. And I had this experience of flow models and writing codes, and I was teaching that course. So we got together and started to write this graphical user interface. And it was so exciting because everything was in Fortran. We learned a language at the time called Turbo Pascal that allowed, it was very similar to Fortran, but allowed the graphics part of it. So it was so exciting because all of a sudden, instead of saying how many lines and rows you want, we had a rectangle and we could divide into lines and view it. Oh, I want to refine in one area, I just move the line and move the line. And then want to put the well graphically. So we were very excited, working night and day besides our degrees to develop this graphical interface for 1 year, which was released in September 1989, the first version. We tested, actually, it was July 1989, we tested the course, people love it. Then they want to buy it, which was not the original intention. But we said, hey, there is a commercial value. So we started a company called Waterloo Hydrogeological to sell this package. And in September 1989, we issued the first 12 copies, which I remember very well. 12 copies, and all of a sudden we felt that we were doing very well as a student because we were selling this package for $500 each. And then it went from there. It was a success. We sold thousands of copies, and we developed other types of software. One was called Airflow SVE, which had very advanced equations for soil vapor extraction. In Airflow, we had the FlowNet Trans, which is to build flow nets for geotechnical and other types of applications. FlowCAD, which was a three-dimensional first version of FlowPath. Then at the time, we start to develop the 3D application, and Bob Cleary said, why don't you instead of developing your own 3D code and you have to prove it's good, get the prestige of USGS, who had released a few years earlier, 2003, or in 1983, ModFlow. And ModFlow was a package to simulate flow in 3D, written by Mike McDonald and Arlen Harbour. And we said, okay, let's just use our graphical user interface and use ModFlow as the engine. And then in terms of path lines, instead of our own, let's use ModPath, which is a complement to ModFlow that USGS had developed. And for transport part, contaminant transport, let's use the MT3D, who had recently been developed by Chunmiao Zheng as part of his PhD. So we put that package together, called it Visual ModFlow. It was the first graphical user interface to combine all three. There was a previous graphical user interface for ModFlow called ModelCAD, released in 1988 by Jim Rumbaugh. He was at the time at a company called Gerrit and Miller, became Arcadis afterwards. A few years later, he released Groundwater Vistas, which became a competitor to Visual ModFlow. And then a few years later, just to complement on that line, became a Groundwater Modeling System, GMS. Those are the three most famous and used up to today for 25 years of continuous development, graphical user interfaces, ModFlow based. At the time, we started in Waterloo Hydrogeologic to offer consulting services as well. One of our first consulting was EPA hired us to demonstrate the difference between using analytical models, using 2D models, and using 3D models for delineating wellhead protection areas. WAPA was becoming a regulation all over the world. In fact, the UK environmental agents determined that flow path was the mandatory model to be used in any application for wellhead protection areas. So the standard was using calculated radius or other analytical methods or 2D. And then we want to show the advantage of showing 3D. We develop a model 40 by 50 columns and rows and 5 layers, which was big for the time, and demonstrate. Now it wouldn't be accepted, but we demonstrated that using a city called Littleton, Massachusetts, as a and it was in the guideline of the EPA. When we start offering services, we realized that sometimes ModFlow, especially at that time, ModFlow evolved. We are going to talk in a minute about that, but at the time, it was just a standard final difference, and it could not represent very well complex geology. We felt the need of having more advanced tools. Not only advanced geology, but for example, density dependent for saltwater and other density dependent concentrations. It was not available. So we started searching for other tools to use in our consulting service. We came across a package called FIFLOW. It was the Berlin Wall just had fallen, and it was an institute, and the former professors there started to their own venture called WASI Institute to commercialize a GIS package, and this groundwater modeling package that they had called FIFLOW was finite element, much more flexible in terms of the grid, and had a graphical user interface for generating the mesh, and you could represent complex geology much better. So we went to visit them and made an agreement. Why don't we bring from Unix to DOS and from German to English and commercialized worldwide? We did that very successfully. Waterloo Hydrogeological was the only reseller worldwide outside Germany and Austria for a number of years, 12 years. And we represented FIFLOW. At the same time, we were developers of ModFlow. And I think up to today, in our use, we use both packages depending on the situation, on the demand. Some clients even demand ModFlow to be used, especially in the US, depending on the user experience and the level of complexity that's needed. We use ModFlow or FIFLOW depending on the job. And it was a very successful combination. At the time, we also did some work with DHI. FIFLOW later, by the way, was sold to DHI, and now it's kept and maintained by DHI very successfully. Early on, we at Waterloo Hydrogeologic had done some work with DHI, developing the first version, Mike-Shi, which is an integrated surface and groundwater model, and we started developing a Mike mod, which was using ModFlow for the flow part. It ended up not being released, but we had this collaboration for a number of years. In 2005, I sold the company Waterloo Hydrogeologic to Schlumberger, who had decided to start working in groundwater. Schlumberger, oil and gas service company, very much experience in subsurface. Why not use that experience in subsurface dealing with groundwater? So they decide to start Schlumberger Water Service, and that was a very exciting time for me because all of a sudden, instead of being in my own company, we had at the time at Hydrogeological headquarters in Canada. That was originally where it started. In Tampa, Florida, uh, Santiago, Chile, and in São Paulo, Brazil. But then it was still a small company. And to be part of this huge corporation, which had plans of expanding and means to finance this expansion. So for the first year, it was a group of 8 people developing the strategy of this new group. In the strategy, we identified a few things. Mining was one place that we should pay attention because through Hydrogeologic subsidiary in Chile, mainly, we saw that water had a huge value in mining because sometimes mining has too much water, so they have to get rid. Sometimes they need water for processing, and sometimes they also contaminate the water through tailings and other process. So water and mining is very integrated and has a high cost. The other area was water supply, and Schlumberger was very well installed in Middle East, and that's where water has a huge value as well. And environment contaminated, especially for organics, because Schlumberger had a lot of tools to identify and measure organics in the soil. And I had some experience in organics because my PhD thesis was not related to any graphical user interface, but it was dissolution of dense non-aqueous phase liquids, DNAPLs, into groundwater, developing a 3D finite element model. We started operations in Schlumberger. Eventually, we acquired who was the main competitor for Hydrogeologic in this mining area, called Water Management Consultants, and became very much into mining. All of a sudden, the group increased from 100 to 300 by this acquisition, mainly devoted to mining. We started the operation of Schlumberger Water Service in Latin America. Eventually, I became a global marketing manager based in Abu Dhabi, where we were involved in a lot of exciting modeling experiences using, for example, dealing with groundwater recharge, artificial groundwater recharge, water supplies, and others. Eventually, I left Schlumberger and became managing director of DHI, where we improve our knowledge and applications of FIFLOW to different areas. And in 2017, started water services and technology with former colleagues from Schlumberger, who at the time at that year decided to get out of the water business and sold its operation in the water. And with some former colleagues, we started water service and technology where I am today. I feel that went full cycle. At the time that I started in groundwater modeler, you needed to know Fortran in order to be a modeler. So that was very limiting because geologists who knew the field and the real world, normally they were not an exact science, they didn't know programming. Mathematicians knew programming, but had no reality checking. They were more concerned about the accuracy of their calculations. But that's how it started. And then with the that's motivation for us to start developing the first GUIs. When we first developed the first GUIs, we had criticism from the people that were at the time leading the groundwater modeling science. They are saying, "Oh, you're putting a gun in the monkey hand. People will not know what they are doing. They will be more impressed with the graphics and not impressed with the accuracy of the calculations. So we had criticism of putting in the hands of people that didn't understand what's under the hood. And I used to say, look, to drive a car, you don't need to understand the details of your engine. If it fails, you call to a mechanics. You need to drive well. The same, you can do the model if you understand the basics of what you need, how to better represent a boundary condition, how far to extend your model, how to represent what's your geology like, and so on. And actually, we saw an improve in the quality of the models by doing that because all of a sudden, thousands of people that actually understood the field could start using and see whether the parameters made sense or not. Groundwater modeling is essentially a multidisciplinary tool. You need to have on your side good geologists that may not be uh, expert in numerical modeling, but they can do a geological model and see whether your representation is the model makes sense, it's the best it can be. You need the geochemistry because also if you deal with geochemical reactions, if you are doing contaminant transport modeling, you need to understand the geochemistry. You may need biologists if you are doing any kind of bacteria, biodegradation, viral contamination, and so on. You need people that understand what's under the hood for numerical models. You need people from GIS to actually get all the data. You need data science to get the data in a proper format for you to consume. So it's very multidisciplinary hydrologists because you need to also understand what are the recharge rates, if the surface groundwater interaction, and so on. So it's very important that you have these multidisciplinary tools. So why I say that we are in a full cycle now, we went the full cycle, because at the time you needed to be a programmer to do modeling. All of a sudden, it was enough to understand the situation and use a graphical user interface. And these days, what is happening is to be a good modeler, you need to understand scripting, to do scripting. At the time, we didn't call scripting, it was programming. Now, you need to have scripting. People are more and more like using Python, FlowPy, and other tools in order to develop scripts that allow the running or entering data or visualization of data in a much more rigorous or detailed way that graphical user interface, as powerful as they are now, they cannot do everything that you need. It's a lot of customized things, and therefore these days, in order to do uncertainty analysis and so on, if you don't combine your understanding of, as a minimum, knowing Python to write scripts, and combine them with graphical user interfaces, which most of them accept scripts written into it, then you are not a good modeler. So my advice to people that want to get into modeling, you need to do the following. First, understand the basics without thinking about modeling. What's a groundwater flow? What does it mean, constant head for boundary condition? Some basic of geochemistry, basic of geology. So understand the basics. Then learn a little bit about numerical methods because at that point you know when to use structure meshes, unstructured meshes, finite difference, finite element. You may not be an expert in writing your own finite element code, but you need to understand the basics. Then get familiar with a couple of GUI, and that's okay because that all these GUIs now they have training online, offline that you can take, and it evolves. You can get GUIs as it evolves to understand others and use. So you learn some GUIs, but also make sure that you get good in Python because it will be more and more needed. The way I see models today, we are still we are much more advanced than we were just 5 years ago. We evolved a lot in uncertainty analysis. There are initiatives like this groundwater modeling decision support initiative, GMTSI. I recommend everybody to look in their website. Uh, I'm proud to say that in terms of uncertainty analysis, we have the fortunate of meeting John Doherty, the author of PEST, as early as we develop and start to commercialize Visual Mod Flow, and invited John Doherty to one of our Visual Mod Flow courses through National Groundwater Association, and he started talking about PEST. We put developers to work on a nice graphical user interface for PEST inside Visual Mod Flow, and that was very user friendly at the time because you can uh, freeze parameters, you can see visually the objective function going down, you can see the improvement of your calibration going from iteration to iteration. So very nice graphical user interface which popularized PEST and brought PEST to light. And then PEST has evolved. Today is one dominant part of doing uncertainty analysis. So it is one of the biggest development. We also increased the ability to have more complex meshes than the traditional finite difference rectangular meshes. ModFlow evolved to have the irregular unstructured grid using Voronoi elements. Then the finite element with FeeFlow was triangular, prismatic. Now it's totally tetrahedral, unstructured mesh. So the meshing has improved a lot. The computer power, of course, improving. We can have more elements or cells in order to better discretize and better represent our geology. So it has evolved quite a bit. But for most part, we are still in the early phases of the potential power of groundwater models. We are still using the traditional workflow. We get data, we put data in a GIS, in a data management systems, then we bring it to a model, then we have a geology that's fixed, and then we play with the parameters, we do calibration, we then determine that the model represents the situation we know, and therefore we make predictions to the future. And that's the standard workflow. Now, and then what we do with this, we do predictions, we make a decision, and we hand the model to the end user, normally a report, maybe the files of the model, and also if the GUI has a viewer, which most of them do now, you deliver the file so they can view on the screen what you wrote in your report. And the way I see that this is evolving is first, geology. Geology, for most part now, is static. You input in your model, then you play with the parameters. You may, from time to time, change the geology, but it's kind of a separate, playing with the parameters and playing with the geology. I think we need to incorporate uncertainty in the geology. So as we do the model is giving, especially now with the use of implicit geological models, we need to allow for uncertainty in geological models. These days we are using implicit modeling more and more, tools like Leapfrog, for example. So what we need to do is to develop various scenarios or the various possible scenarios of the geological model and incorporate that into your uncertainty. Not only uncertain the parameters as we are doing most of the time, but combine it for each ensemble of your geology due the uncertainty in the parameters itself. That's one thing. The other thing, of course, as the computer becomes more and more powerful, you can have more details uh, and less decrease the uncertainty. For example, dispersion. Dispersion, it's bigger dispersion as large as you go because the dispersion in a lot of cases is the fact that you represent a heterogeneous model with one homogeneous cell, and therefore there are some faster velocities, slower velocities. If you could represent at the pore size, there was no need for dispersion, but that won't be possible for near future. But as you decrease that uncertainty, or not uncertainty, but as you decrease the detail of the geology, that's one parameter that will be more assertive, dispersion. With the more powerful computer, and therefore today even, what is the idea? What's the norm in a consulting world at least? You run in your PCs, maybe in the network of your PCs using parallel computing, and that's as far as you go. More and more that you will need to use the cloud to do that. So I think in the future, all models will be done in the cloud. Parallel model runs with all these uncertainties and provide a range of possible scenarios so the decision maker can use maybe the most likely worst scenario or using the average scenario depending on the situation. So you are going to run these models on the cloud, and maybe a lot of them will start developing a software as a service. So you can you don't need to have all these powerful computers in your own company. The other part that we need to evolve is in terms of dealing with climate change. It's more and more imperative that we combine with hydrological models to see how climate changes and how extreme events and others will affect your groundwater recharge rates, what's the interaction between groundwater and surface water. And that's one area that still very few practical models are available that people use combined surface and groundwater. So more and more, I think these models will be holistic. In terms of machine learning, to get based on historical data, do more assertive predictive analysis. And that's one area that is growing. It's already being used, but it will grow more and more. Graphical user interfaces that will allow the end user that's not a modeler to play with scenarios. So the way I envision is transparent models that the end user will see on a screen the current scenario. And if he wants to add a well, he goes there, add a well. Behind the scenes, the model is running, provide him the data. Also, combined with that, the receiving of data. So right now, more and more people are using sensors, and more data is coming, and the assimilation of this data with the model and do the prediction in a take into account this new data, it and assimilate this data and do predictions, that will be more and more common. So this transparent model will receive the data, the sensors, use machine learning to see the next step, maybe identify the need of changing some parameters to calibrate the near history, the past near history, and then be ready for the end user to move things and see the effect. We are not that far to have models built with agents. So right now you have to build a groundwater model, have the groundwater interface, and a lot of people are saying, "Oh, I don't want to use GUIs. I want to use FlowPy and do my model." There are disadvantages because first, when you build, usually you don't put much error checking, which GUIs have been for the 25 years being developed, and there are a lot of error checking. Also, you build a FlowPy for your specific scenario. Next model that you're going to build, you're going to rebuild everything. And the graphical user interface allows you to be more flexible. If, for example, in ModFlow, you want to use NWT or you want to modify to ModFlow 6, that's no problem. But in your FlowPy, you had to review everything. But with the advance of these agents, it will be, I think it will get to the point where you are going to create prompts. Build me a groundwater model for this geological model and give the parameters you want to be uncertainty. And there will be tools that will, on the fly, build a model and display the results the way you want without needing to use a standard GUI. But that is the next step to use the GUI is to use these agents instead of GUI to do that. Another area of advancement will be the simulation of contaminants or chemical reactions. Right now, most of the models for contaminants are non-reactive components or simple reactions. More and more, there will be the need to do, for example, acid mine drainage, changes in pH, and it will be thermoequilibrium simulations using thermodynamics. So tools like FreakC integrated with 3D models that will be more and more used. And the other tool is the integration of models with geotechnical parameters. Incorporate subsidence, changing porosity, changing hydraulic conductivity according to subsidence, so on. At Water Service Technology, we recognize the need to have a multidisciplinary teams to do good models and present solutions to our clients. And that's why we have in the team hydrologists to better understand the relation between surface and groundwater, hydraulic engineers to better understand potential of floods, design drainage systems, flowing canals and rivers. We also have geotechnical people because we need to understand the effect, for example, in porosity due to subsidence of compaction of tailings. We need geochemistry people in order to better represent the reactions, for example, in acid mine drainage and others, that what happens with this thermodynamics in the system. We also need the GIS people to bring the data. We need the data specialists in order to organize and evaluate do QA/QC of the data that's going to feed the model. And we also have developers in order to continuously develop scripts, bring artificial intelligence tools, predictive tools inside the model. In my career, participating in several rewarding projects that I'm proud to say. A couple of them here in Brazil, we developed CIAGAS, which is the National Groundwater Information System, which today has about 350,000 wells implemented. We had developed, with the help of Canadian International Development Agency, the first version, still at my time at Waterloo Hydrogeological, and then we developed the second version when I was already with Schlumberger, which is the version that's being on the site of the Brazilian Geological Survey these days. Still in the Northeast Brazil, we were involved in a project called PROASNE, which is Northeast Groundwater Program, also under the help of Canadian International Development Agency, where we did develop systems to identify better locations for implementation of well, and also groundwater models to assess the potential of agricultural development in a state called Rio Grande do Norte. Outside Brazil, also, I was involved early on, since the year 1999, and then back in 2008 and 10, in the project Great Man-Made River in Libya, which was extracting water from the desert, 1,000 kilometers south, close to Chad, and bringing all the way to Benghazi and Tripoli, and along the way to build a corridor of irrigation. And it was the largest engineering project. So our role there was to assess if such a project could sustain water for how many years, and if it was sustainable. Not sustainable in a sense because it's fossil water, but if at least could operate for decades at the planned extraction rate. It's a project that is still in operation today after all the wars and things that happen in Libya, but that's the main water supply for the country itself. When I was in Abu Dhabi, being involved in artificial storage and recovery, Qatar has a plan of injecting groundwater into saline aquifers and create a reservoir of fresh water of 3 years of supply. So we're involved in doing that. To illustrate the usefulness of groundwater models, we recently worked on a project where in a coastal city, every summer they would have lack of water because they would consume double amount of water than in the rest of the year for a concentrated period of 4 months. Then one idea was why don't we take extinct quarries, sand quarries, and start extracting water from these lakes that form the same sand quarries, but we had to see whether this was sustainable. If we would extract, what was the groundwater recharge rate to these quarries, so that it could be continually supplying water to the city during that period at least. We did a groundwater model. We had 2 months to complete the project and take the data, do the groundwater model, and make a decision. Based on the decision, the municipality built expensive water treatment plant, and besides these 3 empty quarries, to supply the water. And now, 2 or 3 years later, we see that what the model predicted is more or less exact to what is happening in the field. It was a very successful project, and now the city doesn't have that problem anymore. So this is the type of applications that groundwater models can do. Groundwater models can be very useful for predicting water supply, predicting movement of contaminants, predicting environmental impact assessment, interface with surface water, climate changes, and many more applications. Recently, we also have been involved in a lot of decommissioning of mine tailings. The recent disasters of tailing dam designs, tailing dam failures, have prompted a more rigorous approach in studies tailings and to decommission a lot of facilities existing. And the study of groundwater interaction with them is very important, because if I just cap, maybe the groundwater will start to flow from beneath, will create a pressure, it won't solve the problem, may make worse. If you dewater, how to dewater? Can you build drainage? Do I need to excavate? How the pressure of the groundwater will affect the stability of the current or new dam to support the existing dams. So we are doing lots of decommissioning of tailings, uh, and groundwater models are very useful to that. There is a growing focus on sustainability and climate change. Understand how climate change may affect groundwater recharge rates, water availability, and groundwater quality is critical to ensure that water is used in a sustainable manner, especially in areas that are affected by drought or floods or extreme events.